Okay, so we're on page 11. We're going to see a lot of the same stuff that we've already been working on with function notation. We've talked about rules already, and we've talked about things like order of operations and simplifying and solving in that review week that we did at the very beginning of the semester. So all of that is going to come in today. So a lot of familiar stuff today. At the top of page 11, we are looking at being able to use function notation to represent different rules that we have described here. As we talked about last week, the reason that we care about notation is because it gives me a nice, concise, clear way to be able to say what I want to say. So I've got descriptions here that say what I want to say. But again, we've got notation that we can use to represent all of these things. So that's what we're going to talk about first, making sure that I understand what it is I'm trying to represent and how the way that I phrase something can change what I want to represent. So just to make this a little easier, I'm going to call this 1, 2, 3, and 4. So as we talk about them, we can say the first one or the second one or number 4. And then let's take a look at our descriptions over here on the right-hand side. A says to get the output, I subtract 7 from the input and then divide the result by 3. These order words are important because that tells me what I want to do first, what I want to do second, what I want to do third, depending on how big my function is. So this says subtract 7 from the input. So take my input and subtract 7, then divide the result by 3. So I want to do this first. One thing I can do to represent I want to do this first is to use those grouping symbols like parentheses. So I want to do this first and then divide whatever I get by 3. What's another way that I could represent this? That's one of my functions over here. Subtract 7 first, then divide by 3. 4, right? Subtract 7 first, then divide by 3. This would match A. B, to get the output, subtract 7 from the input, then multiply the result by 3. Which of our functions would match B? Subtract 7 first, then multiply. 2, yeah, those grouping symbols, right? Tell me I want to subtract 7 first. If I didn't have those there, this would tell me multiply by 3, then subtract 7, because I would be relying on order of operations. So anytime I want to do something different than order of operations, I need to make sure I'm using those grouping symbols. C, to get the output, multiply the input by 3, then subtract 7. Let's see, which is this one? Number 1, multiply by 3, then subtract 7. I don't need grouping symbols here because order of operations tells me to multiply first, then add or subtract. And then finally, D, to get the output, divide the input by 3, then subtract 7 from the result. So obviously that one's going to be 3. It's our only option that's left. But this says divide by 3 first, then subtract 7. Again, order of operations would tell me do the division first, then the subtraction. So the subtraction is written outside of the division. That's different from how we had it represented in number 4. Okay, that's the difference there. What am I doing first? Then I'm doing this next thing. So using the functions that we have here at the top of page 11, let's go back to our sort of function notation and evaluate work from earlier. So we did this, we matched each function with its description. And now I'm asking you some questions about input and output for these different functions. Remember, input would be an X value when I'm talking about a function, and output would be like a Y value, or after I simplify, what do I get? So for number 2, it says, which of these functions has an output of -3 with an input of 6? So we worked a lot with inputs and outputs in the last few days when I had a table or a graph or one of those relation maps, but not so much when we had an actual equation or function here. So that's going to be the piece that we add in for today, okay? So what this means is that I'm going to plug in x equals 6 to each of my functions, okay? and then look at their outputs. So for my function f, okay, we're going to do f of 6. That means we're going to plug in 6 for x. So that would be 3 times 6 minus 7. And I'm going to use order of operations to simplify. So 3 times 6 would be 18, minus 7 would give me 11. As we're working through our problems today, some of these may be problems, especially later on in class today. Some of these are going to be problems where if you were working on them on your own, I would expect that you would probably pull out a calculator to help you with some of the simplifying, and that's okay. But the simplifying and typing things into a calculator is not our focus for today. So I'm going to help us with a lot of that simplifying just to make that part of it go faster so we can spend our time on the function notation, the inputs and output stuff, okay? Next, we've got G, so G of 6. That would be 3 times, in parentheses, 6 minus 7. Again, I'm plugging in 6 for x. So I'm going to work inside parentheses first. Remember, order of operations as we're simplifying. 6 minus 7 would be negative 1. 3 times negative 1 is negative 3. Now I'm going to keep going. H is next. So I want H of 6. So that would be 6 divided by 3 minus 7. Again, follow order of operations as we're simplifying. So 6 divided by 3 would be 2. 2 minus 7 is negative 5. And then finally, k is our last function here. So I'm plugging 6 in for x. That would be 6 minus 7. And then all of this divided by 3. On top, 6 minus 7 is negative 1. Negative 1 doesn't divide evenly by 3. So I'm just going to leave this as negative 1/3 there. Fractions are okay. So we just practiced taking an input and plugging it into a function. Okay, 4 times we just did that. Now this asks me which function has an output of negative 3 when the input is 6. So yeah, G has an output of negative 3 when the input is 6. Very good. Number 3, same idea, but this time our input is 0. So we're going to plug in x equals 0 to each of our functions this time. So f of 0 means we plug in 0 for x. So 3 times 0 minus 7. 3 times 0 is 0. 0 minus 7 would be negative 7. And then g of 0, that would be 3 times, in parentheses, 0 minus 7. 0 minus 7 is negative 7. Remember, in parentheses first. And then 3 times negative 7 would be negative 21. And then h of 0, this would be 0 divided by 3 minus 7. 0 divided by 3 is 0. 0 minus 7 is negative 7. And then finally, k of 0. So this would be 0 minus 7, all divided by 3. On top, 0 minus 7 is negative 7. And then negative 7 doesn't divide evenly by 3. Since this is reduced, I can leave it as that improper fraction if I wanted to. Our goal here is to decide which of these function values is greatest. So if it's helpful for me, I can change this to a mixed number as well. So this would be negative 2 1/3. So which of our functions gave us the greatest value here? Which of these outputs is biggest when I've plugged in 0? K, right? I've got all negative outputs this time. So if I thought about this on a number line, I would be looking for, since we're all over here, which value is furthest to the right? And that would be K. Now, number 4 is asking a similar question, but this time our input is 10. I would like you to try number 4. Okay, we just did 2 together, so you try number 4. Okay, after finishing up here, f of 10, when you plugged in 10 for x, what did you get? 23. How about for g? G of 10. 9. How about h of 10? You could leave this one as a fraction. Yeah, this would have been negative 11 over 3 if you left it as a fraction, or negative 3 2/3. How about k? K of 10. 1. Good. So which of these had the greatest function value when our input was 10? F did, right? Now, let's see, challenge problem down at the bottom says, is f of x always going to be greater than g of x? If I look at the inputs that we've used so far, those values we've plugged in for x, my value for f has always been greater than our value for g. We had 11 compared to negative 3. Negative 7 is bigger than negative 21, and 23 is bigger than 9. I want to know, is this always going to be the case? So f of x, just so I've got it down here to look at, is 3x minus 7. And g of x is 3. And then in parentheses, we're multiplying by x minus 7. Now, if you remember sort of vaguely from the last time you did some algebra in a math class, this is what we call slope-intercept form for a line. And then this guy we could call point-slope form. We talked about slope-intercept a little bit earlier this year, but we haven't done point-slope together yet. I know you may have seen it in maybe 8th grade, but it's been a minute. So what we can do here, so that we're kind of working on a level playing field, is let's distribute this to get slope-intercept form. So that would be 3x minus 21. So 3x minus 7 and 3x minus 21. I want you to notice these lines have the same slope. Do you see that? 3x and 3x, same slope, okay? What does that tell me about these lines? They have the same slope. They are parallel, yeah. So what we've got is something like this. Here, our y-intercept would be at negative 7, so let's say that that's here. And my line looks something like this. Now for g of x, our y-intercept is negative 21. That'd be down here somewhere. It has the same slope because it's parallel. Okay, but it's going to be down here because its y-intercept is down here. Now, when I say, is f of x always greater than g of x? What I mean is if I pick an input, is that value I get on f of x always going to be bigger than the value I get on g of x? Yeah. Back here, I'm going to hit the f of x line before the g of x line. Here, I hit the f of x line before the g of x line. Because f has a greater y-intercept, whatever value I pick, f will always have a greater function value than g. Okay? So I could have plugged in a bunch of function values and kept checking. We already had a few examples here, but we can also tie that back to what we would see if we looked at a graph of these two functions. Okay, all of this stuff works together. If you would for me, please, turn the page. On page 12, we're going to take a look at another problem where we're going to figure out a rule and use that rule to write a function. Okay, so we haven't written our own functions yet. We're going to start that now. So at the top of page 12, problem 1 says a square that has a side length of 9 centimeters has an area of 81 centimeters squared. Does that make sense? Does that check out from what you guys learned in geometry last year? The side of a square is 9, its area would be 81. Yeah, how do you find the area? Length times width, right? So if I'm looking at a square, okay, and its side length is 9, its length and its width are the same. 9 times 9 would give me an area of 81. That seems reasonable based on what we know from geometry. The relationship between the side length and the area of the square is a function. Complete the table with the area for each given side length. So let's start over here. We've got a bunch of examples that we're going to talk about. So let's say my side length is 1. What would be the area of that square if the sides are 1? 1, right? 1 times 1 is just 1. What if my side length is 2? What's our area then? 4. What if the side length is 4? Our area is 16. What if our side length is 6? Our area is 36. Now let's generalize this. Let's write a little rule here. What if it's just, let's use the S for side length. How could I find that side length? What would I do? Something like that. Go ahead. Yeah, S squared, right? We're doing side times side, which would be an exponent of 2 or S squared. So with this little sort of rule, picking out my pattern here, we can write a function. So it says let our function be A, probably A for area. And we'll let our side length be S, so A of S equals S squared. So the area based on the side length of the square would be S squared. And there's my function written using function notation. Now, number 2 throws us back to some stuff we did earlier, right? I've written a function here using function notation. Let's talk about what something in function notation would mean here. So number 2 says, what does A of 2 represent in this situation? What is its value? So A of 2, for this problem, we're talking about areas of squares. What is the 2? Let's start there. 2 is the side length, right? 2 centimeters, okay? So a square with a side length of 2 centimeters. And then what's the A part of this? The area, right? So what we're talking about here is the area of a square with a side length of 2 centimeters. And then the second part here says, what is its value? So A of 2 is equal to what? 4, right? From our table, side length of 2, area of 4. So our area is 4 centimeters squared. So we've got a table here that we could use. A of 2 equals 4. be able to answer some of these notation questions, evaluate based on inputs and outputs. We did that before, right? We've seen lots of examples where we have our information in tables. Remember, if I have representation in a table, I could also have representation in a graph. So I've got side length here on my x-axis, area here on my y. So I could take all these values from my table and plot them in a graph. So 1, 1, 2, 4, 4, 16, 6, 36. I could even, based on my function, fill in some of these values that weren't in my table. 3, 9, right? 3 squared is 9. 5, 25, since 5 squared is 25. Okay. And then I could also ask questions using my graph about inputs and outputs. Now, this wouldn't be a great graph to use because our y-axis goes by tens. I'd have to do a lot of estimating here if I didn't have the function. But anything I could represent with the table, I could also represent with the graph, which we said we could also represent with our function here. Okay, again, all of this ties together. So if I can evaluate functions with inputs in one version of this, I can do it with another version. Let's take a look at another problem. Down at the bottom of page 12, problem 2, we've got a roll of wrapping paper that is 3 feet wide but can be cut to any length. So the situation here is we have our tube of wrapping paper, right? And the wrapping paper tube is 3 feet. So once all the wrapping paper is gone, the tube you have to use as a lightsaber and hit your siblings with is 3 feet. Does that make sense? Okay, I see some smirks. We've done this before. I know, we did it too. Okay, so my future lightsaber is 3 feet. Now, right now, it's got all this wrapping paper rolled around it. Okay, and the idea behind the wrapping paper is I unroll as much as I need to, cut it off, wrap my gift, and move on with my day. Now it says we can cut this to any length. So let's say we cut off a piece that is 2.5 feet long. So here's where I cut before, and I need a piece that's 2.5 feet long. Okay. I want to know what would be the perimeter of this sheet of paper that I am going to cut off to use to wrap my present. How do we find perimeter? I add up all the side lengths, right? So this edge that I'm going to cut off the tube, that's going to be 3 feet, right? Because my tube is 3 feet. This, edge where I cut last time, also 3 feet. And then my top edge here is 2.5. And my bottom edge will be the same. So I'm going to add up all those sides to get my perimeter. So this would be 3 plus 3 is 6, 7, 8, 9, 10. And then my halves get me to 11 feet. My perimeter for my sheet of wrapping paper would be 11 feet. So I've got one example here. Let's use this same idea to create a table. So we've got a couple more examples. So let's say our side length is 1. So not 2.5 anymore. We're going to change it to 1. Okay. We're still going to have 3 and 3. Does that make sense? I didn't roll it out as much this time, but the tube hasn't changed. So 3 and 3. Now plus 1 plus 1. So this would be 6, 7, 8 for my perimeter. Now let's change the side length to 2. What changes about what I add up here? How am I going to change this if my side length is now 2? I heard plus 2 instead of plus 1, right? The 3 stay the same because my tube isn't changing, just the amount of paper I'm pulling off of it. This would be 6, 7, 8, 9, 10. I would like you now to find the perimeter for 6.3 and for 11. So if I unroll 6.3 feet, if I unroll 11 feet. Okay, what's our perimeter if we unroll 6.3 feet? 18.6, perfect. And then I'm gonna wrap the largest present in the world and I need 11 feet of wrapping paper. What's the perimeter there? What did we say? Sorry. 28, yeah. Now, let's come up with a rule that represents this. We'll let L be our side length. The 3 plus 3 stayed the same for each of these, right? So I would keep 3 plus 3. As I change the side length, these other two numbers change. So this would be plus L, whatever I decide to let that be. Can I tidy this up at all? Maybe make this a little more concise. What's another way I could write this? Not quite. What is 3 plus 3? 6, right? So we can do 6 plus, and then I want L plus L. Now up here we said S times S with S squared. Since I'm not multiplying, it's not going to be a square, but it will be 2L. Does that make sense? Okay. So 6 plus 2L could be my rule for that. Now this is a function, so we can use this information to be able to write a function. Okay. My function P, probably P for perimeter. So my function P gives the perimeter, yep, of the paper in feet when the side length is L. So we're going to use P of L here equals 6 plus 2L. And that would be our function using function notation. Now again, let's interpret this. Notation is only helpful if I know what it means. Okay, we talked about that before. What does P of 11 represent in this situation? So P of 11 for this function I just wrote, what is that talking about? What's the P part referring to? Perimeter. And then what's the 11 mean? Yeah, so I'm looking at the perimeter of the paper with a side length of 11 feet is our unit here. And then it says, what is the value of this? So P of 11 equals, you did this already, 28, yeah? So 28 feet would be our perimeter. Questions for me so far? Okay. So we have talked about using tables to find input and output. We did that again here just now. The next thing that we're going to do some practice on is using our functions when we're talking about inputs and outputs. Okay. A couple of the things that we struggled on our last quick check. One, making sure we were looking at the right function. So I may have asked you something about f of x, but you told me something about g of x. So we need to make sure we're looking at the right function, and we'll talk more about that as we go through page 13. And then the other one is making sure I'm paying attention to if I have an input or an output. Okay, is this an input value or an output value? Remember, input is x, output is y. When I'm looking at a graph or a table, input is x, output is y. If I've got one of those maps, then input is my first sort of column or whatever we want to call those little boxes, and then output would be the other one, second one. When I've got a function, like what we have here at the top of page 13, input would be our x value, output would be, I plug in an x and see what it simplifies to. So we've got b of x equals 10x plus 25. So I need to make sure where it says b that I'm using this function. Okay. And then I need to pay attention to, is this an x value or an output, a y value? If I have replaced the x in parentheses with a number, that means you are going to replace the x with that number in your function. Okay. So instead of x, I have 6 here. That means I'm plugging in x equals 6. Okay, so for A, this is telling me plug in 6 where you see an x in your function. So this would be 10 times 6 plus 25. And then tell me what the output is. So let's simplify this now. Remember to use order of operations. So 10 times 6 is 60, plus 25 would give us 85. So my output would be 85. I knew the input, I found the output. For B, this time that part in parentheses is blank. I don't know what that is, but I know it equals 93. So since I'm setting this equal to 93, I have an output. That's exactly what I want to do with my function here. 10x plus 25 equals 93. So over here, we replaced x with 6. So we did the same thing in our function. Over here, my function is equal to 93. So that's what I do. I set my function equal to 93. Excuse me. Now what we're going to do is solve for x. So we did some practice with this at the very start of the school year, very beginning of the semester. Remember, as I'm solving for x, I'm sort of unraveling and I'm working through order of operations in reverse. So I'm going to start by subtracting 25. And I get 10x equals 68. And then I'll divide both sides by 10. So we get x equals, I'm going to use decimals here since we're dividing by 10, 6.8. So that was my input. If x is 6.8, I would get 93 as an output. For C, 2.75. Do I plug that in for x or do I set the function equal to it? Plug in or set equal? Plug in. It replaced x, so I'm going to use it to replace x. So 10 times 2.75 plus 25. 10 times 2.75 would be 27.5. Nice thing about multiplying by 10 is it makes those decimals not so tough. And then if I add this together, I would get 52.5. For D, B of something equals 116.25. So what do I do with this number? Plug it in or set it equal? Set it equal. So 10x plus 25 equals 116.25. Remember, we go through reverse order of operations as I'm solving for x. I'm going to move the 25 first, and I get 10x equals 91.25. And then we divide both sides by 10 to get x by itself. That would mean move the decimal one spot. We would get x to be 9.125. Okay, so I need to pay attention to, do I have an input or an output? And then this new piece here, working with a function, I'm either plugging something in for x, or I'm setting the whole function equal to that output. 4 is back to a graph, and we've seen graphs before. So again, we want to pay close attention to, do I have input or output? So f of -5, this is an input. This is an x value. So I'm going to go to where x is -5 and follow that to the graph and report the y, report the output. So that would be an output of 1. So f of -5 equals 1. For B, f of -1, again, that's an x value. So I'm going to go to where x is -1. And then my graph is right there. What's my output for when I have f of -1, I should say? 0. Good. My y value is 0. And then finally, f of -3, -2, -3. Okay. See how I want to say 1, but it's actually an open circle there? Open circle means it's not that value. If I hop up to 2, I have another open circle. So it's also not 2. What is it? Yeah, we have this point hanging out down here. That's where I have a point when x is -3, y is -6. Good. Now for D, E, and F, this time I've got the outputs. We want to find the inputs. So d f of something equals 4. So I'm going to go to where y is 4. Follow that to my graph, and there's my point there. X is -6. For e, f of something equals 0. So here's where y is 0. Now we already talked about one of these points, -1. But if I look, I have another spot where my y value is 0. So I need to report that -4 as well. Okay. We talked about this before. If I've got more than one place where this is the output value, I need to report them all. And then finally, 1. So here's 1. I've got a point on my graph here at -2. And then I've got an open circle here. Do I report that one? No. Open circle means this is not a point. But I do have another one here at -5. So I'm going to list -5 here. So this graph is an example of a piecewise function. I've got different sections of my graph that behave differently. We've seen piecewise functions on graphs before where I've got different chunks that do different things. Down at the bottom, we've got a piecewise function, but given as a function instead of on the graph. So same idea when I had to be careful about which function was I talking about. Am I talking about G or F or K? I need to be careful about which section of my piecewise function I'm looking at here. So I pay attention to what that X value is and which of my categories it falls into. So my first X value, remember, since it replaced the X, it's an X value. My first X value is 10. That would be this bottom section where I'm greater than -4. So that means this is the part of the function I want to use. 1/2 times 10. So that would give me 5. 1/2 of 10 is 5. For my next X value, -8, not this bottom section because that's not bigger than -4, not the middle section because that's not equal to -4. I want this first section, X values that are less than -4, that's -8. So negative, in parentheses, -8 plus 7 squared plus 3. -8 plus 7 would be -1. -1 squared is +1. But this says make it negative. And then -1 plus 3 would be 2. So my output there would be 2. And then finally, f of -4. When we're equal to -4, we're using this middle section here, and that says it's just 5. You don't need to plug in, you don't need to simplify, it's just 5. We've got one more piecewise function here. This time we're looking at X values less than -1, equal to -1, or greater than -1, and up to 2. So if F is equal to -1, I want to use this middle section here, and that says it's just -2. Don't plug in, don't simplify, it's just -2. F of -5, I want to use this first section, so that would be 6 times -5 plus 5. 6 times -5 is -30, plus 5 would be -25. And then finally, f of 0. So that's between -1 and 2, so I would just plug in my value there, and there isn't really any simplifying to do, so my output would just be 0. Your homework for tonight, pages 14 and 15, be careful at the bottom of page 15. You've got 3 different functions there, and one of them is piecewise. So pay attention to which function you have. And then if you have f, make sure you're plugging your x value into the right piece of that piecewise function.